Hey everyone, the Rust Review is back. I'm Brandon Konkle, and I'm excited to kick off this podcast again after a lengthy hiatus. Rust has continued to be my favorite programming language because of the unique way it tracks value ownership and lifetimes, provides strong memory safety, and the kind of language features you would expect from a high-level language, but built on top of awesome low-level performance. It's outstanding, and I'm starting this podcast back up again to help me keep track of current events in the Rust language community and share what I learned with all of you. I want to highlight news and articles and posts and projects and let you know what I thought about them. And I'm doing my work to research each item that I highlight and try to find the appropriate context and really dig in and try to understand what I'm talking about. I may do a greater or lesser job of that, and you can let me know in the comments what you think and what I got wrong. I'd love to hear from you. Each week I'm going to sift through sources like This Week in Rust, the Rust subreddit, the Rust tag on Mastodon, Discord, fellow Rustations, and more to find interesting topics to share with you. And today I'm going to kick off the show with a really interesting post from Saoirse. Saoirse at the Without Boats blog. They are somebody who is rather well known around the Rust community. They are prominent contributors to the development of Rust. They've been deeply involved in the community, contributing to language design, libraries, the overall ecosystem everywhere. And this post is kind of similar to the one that I covered about a year and a half ago from Joshua White's deep diving into why async Rust works the way that it is. And Saoirse had their own post about that last year as well. This one specifically focuses on pin, which I think pin is one of the more confusing parts of async because largely I think we don't always have to think about it. If everything is going smoothly, then it's all behind the scenes. But when we need to jump in and work on our own future implementations, or when we're trying to solve issues with references or lifetimes that aren't working the way that we expect, pin can be kind of a confusing part of that. Mostly what Saoirse says is due to a surface area, an API it's really unfamiliar. It's not obvious to people just by virtue of having been Rust engineers. It's something that it has its own thing, its own terminology. It doesn't work just in obvious ways like a mutable reference would, for example, or something like that. So I knew Rust wasn't perfect, and there's always going to be things that could be done better. This post, Saoirse acknowledges that pin is a bit of a mess and it's their fault. Not entirely. There's a lot of people's opinions that go into it, but they were definitely deeply involved in this, and they acknowledge the criticism is valid. They acknowledge that there is a complexity spike. In fact, Saoirse calls it a complexity cliff, as if the user suddenly finds themselves thrown off a cliff into a sea of complex, unidiomatic APIs they don't understand. Before we get to what the problem with pin is, though, Saoirse first goes into what does pin actually do? Why does it exist? And what problem is it solving? And I love this. I love articles like this where somebody who has direct experience in the implementation talks about the factors that go into it, because it's always more complex than you expect from the outside. It always seems to involve more variables than you ever would have imagined. And this is definitely the case with pin. So the problem, or I guess the problem that pin solves, the reason pin exists, comes down to how async works in the Rust ecosystem. Rust provides some primitives for asyncs, but then there are different implementations, different runtimes for async in the community. So the one that has definitely won the most broad adoption is Tokyo. Tokyo is the clear winner, and for good reason. It's excellent, but there are alternative implementations. Some of them have been losing speed over time, but there are others that solve a specific need. So things like embedded environments where Tokyo uses libc, but that's not available in an embedded environment. There are async runtimes that solve that problem. But ultimately, it's comes down to a syntactic sugar around async await that expands. It compiles into something more complicated, something that we don't have to see behind the scenes most of the time, and something that differs a little bit depending on the async runtime that you're using. So the actual code that is generated may look a little bit different for Tokyo than it does for something else. But essentially, Saoirse provides a simplified example here, an example that shows a struct here, this bar struct. This is meant to represent the future. So this bar enum is a future, and the enums represent the different phases that the state machine can be in. So Rust provides kind of the boilerplate core pieces of an async implementation, which involves a rather complicated state machine, because the job of balancing tasks and polling for status and handling different results is a really complex business, and you have to keep track of a lot of things along the way. So if you look at these two functions here, just like a regular function in Rust, the type signature of these functions are anonymous. So you can't say like just a regular function bar has a named type or anything like that. It's an anonymous type that Rust keeps track of internally, but you can't refer to from inside your code. But Rust makes sure that the type is consistent with the ways that you are using it. So async functions are really similar. They compile down to a future, and that future has an anonymous type also, and it's going to be specific to the runtime implementation that you pick, but it's going to look something like this, the simplified example. So when you first construct a future by calling an async function, it doesn't do anything yet. It just sets it up, gives it everything that it needs to begin working, and then sets it aside. And that act of setting it aside is a really important part of this concept here. Rust doesn't have a function stack frame that it's keeping these values in. It has to set it aside somewhere, and where it sets it aside to is going to be different depending on your runtime implementation. So Tokyo is going to put it into an event loop or queue that's potentially multi-threaded, but another implementation might do something totally different with it. And so it holds on to the pieces that it needs to begin executing the function up to the first await point. And essentially each one of these phases of the state are going to represent the work done in between, or I guess the data that you need to resume from each await point to the next await point. So you can see bar takes this X and Y 32-bit integer, and it holds on to it. It has this initial phase in its state machine that is the start phase. It's not always called that, but this essentially is the information that it needs to begin executing the function. It needs to hold on to those arguments, and so it keeps a reference to those arguments inside itself, its struct. So from that point, when you await it, the first time that you await it, it proceeds to this first await point here. So it begins executing it. It creates this mutable value Z that is the sum of X and Y. And then it passes a mutable reference to that Z value that bar owns into foo. And then you can see foo takes that mutable reference. It does something to it. We don't know what. It's clearly acting by side effect though, because it doesn't return anything. So it's mutating that Z value that it gets from the outer future bar. And so from the execution of the function up to the first await point, the things that it needs to keep track of are that Z, the Z value that it owns. Bar is the owner of that. And then foo, the future that bar kicked off and began awaiting. And so you can see that it has a reference to Z, which it owns. This is the core value. It's not a reference, but then inside foo, there's a mutable reference to Z. So the way that you can think about this is bar contains a field foo that references another field Z on bar. So that's what Saoirse and others in the Rust community called a self-referential value. Bar contains a field that references another field on bar. It's circular. It's dangerous when you try to move bar. The problem with this is if inside bar you have a reference to bar, but then outside bar you move bar, the reference inside bar no longer points to where bar exists. So you can think of bar as being this future value that gets constructed inside a function stack frame. And then if it gets handed off to another function before it's awaited, then it gets moved to the stack frame for the new function that it handed off to. And so if that were to happen after it's been awaited, after there's a foo reference now that also references back to bar.z, then you're going to end up with either a null pointer dereference or an out of bounds memory access or something like that. And we all know Rust isn't going to allow that. Rust is going to, through the compiler, make sure that that's not possible. And so that's where pin comes in. Before pin, it wasn't really safe to mutate self-referential types because it could be moved and you would be left with a dangling pointer. So it was really essential for them to figure out how to prevent bar from being moved. But one important distinction here, and they talk a little bit more about this later, is that it doesn't have to always be immovable. It only needs to be immovable after it's begun being awaited. So once something is waiting on it, that kicks off the polling for status, that kicks off the execution, and then in each point between await, it has to set the data aside that it needs to resume or continue that execution after it's ready for the next state transition. So it can be moved before it's awaited, but after it's awaited, that's when you've got the reference to foo and anything else that could be derived from foo. You've got to prevent it from being moved there. But one of the things they considered first was maybe we don't. Maybe you don't actually have to prevent it from being moved. What if you used a move constructor? And this is a really interesting idea to me. Despite the fact that it's called a constructor, it doesn't really have anything to do with the classic kind of like class constructors or new functions that you would see in a different high-level language or something. Really, it's more like a lifecycle hook. So it's really similar to drop. If you're familiar with the Rust drop trait, it's a trait that you can implement that will then trigger some code to run when your value is dropped or deleted or removed from memory, dereferent or unallocated, deallocated. That's the word. So the idea was similarly to how you could have something that runs when a value is dropped. What if you could have something that runs when a value is moved? So then there could be some code to fix up any of those self-referential pointers inside bar when you're moving bar so that they now point to the new location of bar. And this was an interesting solution, but ultimately Saoirse explains that the problem was that those pointers could exist anywhere, like they're saying here, not just inside the value being moved. So if you were going to add some code to the move constructor to handle the move and update all of these pointers, you need to be able to keep track of every place that there was a reference to bar. You need to keep track of all of your references, almost like you're counting those references to see how many references are there before you can deallocate that. This is going down the road, if you couldn't tell, to garbage collection. And garbage collection isn't something that they wanted for Rust. You would need the same kind of map of all of the memory in order to remap that memory. And so you need the same thing that you would need for garbage collection. So that was tossed. Additionally, they determined that adding move constructors would be a breaking change for Rust. Rust actually, they explained in the article early on, came out pretty heavily against the idea of move constructors and said they would never have move constructors. And so there's a lot of unsafe code based on that assumption, based on the commitment or the guarantee that Rust gave early on that they weren't going to have move constructors, because that would complicate a lot of this unsafe code that is based on these assumptions. So that would have been a breaking change for Rust. And Rust guarantees that if a crate, a library is compiled at some point, it'll still compile afterwards. The backwards compatibility is a strong commitment from Rust. And so This means that changes to the language or the standard library shouldn't break existing code, and this would break existing code. Saoirse explains why new editions of Rust, like the 2021 edition, things like that, they can make additions to the syntax and compiler features, but not in a way that breaks existing code. And I think this can be really painful at times, but I think it's the right compromise for the real world users of Rust who want to take advantage of new features without constantly refactoring old code when it breaks. If you were ever a part of the TypeScript community back when we were doing ECMAScript compiling and transpiling, and you might have to go back and rewrite a whole section of code because the way that the syntax worked changed, breaking all the old implementations. And so you'd have code rewriting tools that we would use to scan in all of our code and rewrite everything. That's the kind of thing that Rust really wanted to avoid. And so that was the inherent limitation here, the constraint that they were working under. So they moved forward from there, trying to find a different solution that wouldn't break Rust in the ways that they had committed not to break Rust. So, oh yes, and they talked about offsets as well. They said offsets were unrealistic as well. But basically, moving on, they came up with the idea that Rust has this idea of a type state. So in Rust, one of the type states is mutability. So here's the quote that I was looking for here. It says, Saoirse says that objects can be in one of two type states. Either they're owned, in which case they can be moved freely, or they're shared, in which case they can't be moved because they have references pointing to them until that reference lifetime expires, and then it's movable again. So to support these self-referential future types we're talking about, they talked about adding a third type state called pinned. That's where this idea of pinning comes from. Is you can have an owned type that can be moved freely, or a shared type that can't be moved until the references to it expire. And now you're going to have a pinned type state, which means you can't move it anymore. So once an object enters that pinned type state, it can never be moved again. And that was the best way to guarantee that you wouldn't end up with a null pointer dereference or something like that. So with that in mind, they first approached it in a different way. They thought, okay, if something is pinned, that means it can't be moved. And so they considered a trait that's similar to the sized trait, how everything has sized by default, but then you can use question mark size to say, oh, it doesn't have to be sized. Same thing with this. This would say everything would get the move trait by default, but you could support pinning by saying, oh, no, this one's not move. This one's question mark move, or saying that you don't need the functionality of moving. It's basically runs up against one of the design decisions that considerations that they made at first, was that it doesn't have to be immovable until it's been awaited. And so there are a lot of valid use cases for moving futures around before they're actually executed and begin being waited for. And so that was going to be a big problem with this move. But then they didn't even get to the point of trying to solve that problem, because they figured out that also adding this move auto trait would not be backwards compatible either and would break existing code. And so Saoirse explains more about why that is. But those were some of the main alternatives that they considered before they landed on pin. And so given these limitations, given these constraints to not break things, they ended up figuring out they needed this pin trait. And so it's a lot like move or the idea of it. You can have an unpinned trait that's a lot like move. You can get a lot of the ergonomics of that move type trait, like I was talking about. But the downside to it is that it's not a built-in part of the language. It's not a built-in part of the syntax. So Saoirse explains that anytime that you need to actually deal with pin, it's a complexity spike, like I was saying, because it doesn't work just like a mutable reference or something like that. You've got to deal with this trait and the methods on the trait, which don't actually, which aren't immediately obvious sometimes because it's something specific to pin. It's something that the other references that you're working with don't have to have, but Saoirse goes through some theories around why that's complex, but this syntactic aspect of it, Saoirse ultimately determines is really the problem with it. The fact that you can't use it the same way as another reference. All of a sudden you have to dive in and learn a whole new API of working with a pinned reference before you can do anything with it. That's ultimately the problem with it. So I probably stumbled over myself a little bit on this. This is definitely the most in-depth dive that I've seen to pin and why it is the way that it is. And I really appreciate Saoirse sharing that. The follow-on post that was made, 4 days later, goes into the second part of it. So now that we've established how did pin end up this way, what's the alternative? What should we do with pin from here to make things better? Given that we can't go back and use one of the alternatives that were considered because they had downsides that weren't going to work in the Rust ecosystem, what should we do? And so Saoirse goes into detail about what we can do to make this better, because it's not always when you're trying to do a low-level implementation of a feature. There are some places where you still need to deal with pins even outside of all that, even when you're using the async await syntactic sugar. And so the proposal that Saoirse goes with is that I'll skip down here a little bit because I'm going a lot longer than I intended to. a qualifier, just like the mutable qualifier on a reference. So you can say a reference is both mutable and pinned, or it can just be mutable, or it can just be pinned. Basically, this native support would make it a lot easier, make it a lot more automatic, and would allow, I think, the different operations that you might want to do with a pinned reference to be a lot more seamless and work just like a mutable reference would or something like that. It would be a lot more automatic. So this article has a great proposal on how that might work. I'd love to see where this goes. And Saoirse even goes back to the idea of a move trait again that was considered. But even though Saoirse was open to the idea at first, once they sat down and tried to figure it out, they figured out that it just wouldn't work well. And really, this idea of integrating the concept of pinned places into the language was better. And I really like how Saoirse describes places here. I'm going to try to find the highlight that I made around places. Yeah, pinned places here. So they talk about the idea that a mutable value in Rust isn't really a mutable value. It's a place where a value can be mutated. So the value itself is controlled by this place that the value is put in, and the compiler keeps track of how that can be used. And so really it's a place that is mutable rather than the value itself. I think this is an apt comparison if you think about Go and how everything in Go is mutable. It's really the same thing in Rust. Everything is mutable, but that mutation can be controlled by where we put that value. And similarly, Rust could enforce the rules around pinned places just like it could mutable places in a way that would be completely backwards compatible. I think it's a great proposal. It's a great idea, and it definitely helped me understand why pinning exists and why it's awkward. There's a good reason for why it's awkward, and there are things that we can do to make it better without breaking backwards compatibility. So, like I said, I know that Rust isn't perfect, but it's a language that is very reasonable. It takes all of these aspects into consideration, and it has ways to move forward to make these compromises usable and easy to work with, and I love it. So I love the quote that Saoirse called out from Kamala at the end here. This was Well, in any case, we exist in the context of all in which we live and what came before us. We don't exist in a vacuum. We didn't just pop into existence and start coming up with things on our own. We are resting on the shoulders of giants, and there's a lot of thought and a lot of reasoning that went into decisions like these that we don't always immediately understand. And we didn't just fall out of the coconut tree. I love that quote. All right, so whew, that was a chunky topic to start out with, and one that I think I stumbled over a little bit, but let's keep that trend up and go into another really big, weighty, heavy topic with a lot of complexity. But I think I've gotten to a point in this where I can sidestep some of the complexity for reasons. So the CrowdStrike global IT outage, largely considered to be the most widespread IT outage in history. I'm not a Windows developer, so I'm not going to do a full explainer into this. I think there are good explainers and a lot of really bad explainers out there. There's a lot of misinformation going on, so be careful who you listen to and who you trust. I will go up front and say, I'm not an authority here. I am relying on the analysis that I've read through, the preliminary post-incident report that we're looking at here from CrowdStrike, Microsoft's blog post that I'll touch on in a minute here, and a lot of other details to kind of triangulate a position here. I think I've done enough research to develop a reasonable opinion on whether Rust itself would have magically prevented the CrowdStrike outage from happening or not. And that's the talking point is, would Rust have prevented the greatest IT outage in history? And the answer, I think, is complex. Of course, it depends. CrowdStrike themselves posted this preliminary report, providing a lot of context around where and how the fault occurred, some additional technical details. People can pull the file up on their machine in a lot of cases and take a look at it. Essentially, this first article was more high level, and it talked about their update process. They use these template types to, let me get down to it here. Yeah, they use these template types. Basically, it has a sensor. This sensor is a threat detection tool that operates at the kernel level. So it's operating in kernel mode. It detects malicious behavior. And so there's all kinds of different aspects of the system that it inspects to determine malicious behavior. This particular error happened around some mitigation or censoring, some detecting that it does around malicious named pipes. You can create named pipes in the Windows ecosystem, and there's a way to abuse that this CrowdStrike sensor watches for. And so the sensor has all of the behavior that it executes contained in these channel files. And the channel files have different template types. These template types are like different types of behavior that the sensor can execute when it is filled in with details. This template has variables that need to be filled in order to define the specific parameters that it wants to execute this behavior within. So this sensor has a template type, and there are multiple template instances that use that behavior, that use that template type to do different things, to detect different kinds of malicious activity. And so when they're releasing these template types, they do some stress testing. They take a specific template instance, so a specific set of filled in values. From what I understand, this is a binary file that gets compiled and deployed to the machine. But this binary file contains a set of values that fill in the details needed to execute the behavior around the template type. So in this case, detecting malicious named pipe creation. So they test the template type with a specific template instance. They do fuzz testing to get any possible value of the associated fields in that template to try to identify these adverse system interactions. But then once they've done that extensive initial testing, they deploy new template instances, new sets of variables or properties for that template without the same kind of stress testing. And I think herein lies the problem. Back on July 19th, they deployed two new template instances. There had been previous instances deployed for this template type around name types before, but on July 19th, they released two more. They both passed content validation, but one of them shouldn't have. One of them should not have passed content validation. And so it got deployed to the sensor. And from what I understand, there was a reference, a pointer inside that binary blob of the config file, or I guess the template instance, that led to, it should have led to a well-known or a predictable region of memory that had something that it needed. So presumably something else from the Falcon tool, the sensor. It should have linked to something within the boundaries of memory allocated for that process. But instead, for whatever reason, because of this malformed template instance, that reference pointed to either unallocated, undefined memory, or something that was owned by something else, out of bounds memory. And especially in a kernel mode driver like this, it's really important to prevent out of bounds memory access, because that could lead to grabbing data that you're not supposed to have access to. It can be really random, but that randomness is not really a hindrance. You saw this with the Heartbleed vulnerability in OpenSSL, where out of bounds memory access wasn't prevented. It didn't cause a panic, or it didn't cause a blue screen of death. And so it was able to eventually, over time, scrape enough data to gather encryption keys and other passwords or information that it needed to compromise the environment. And so that's what a blue screen of death like this is intended to prevent. So you've got a really low level process. It's running in kernel mode. It's trying to reference a predefined region in memory to grab something that it needs in order for executing that template type, the behavior, the pre-programmed behavior that it was doing. And because the data was malformed, and because it wasn't, that particular template instance wasn't tested as much as the first template instance of that template type, it ultimately resulted in an out of bounds memory read, and it triggered the worst kind of exception, a blue screen of death. And it's the worst kind of exception because you can't recover from it. Not only can your process not recover from it, you can't catch the blue screen of death and handle it. No other process on the system can't, because integrity may be compromised. If something reached out and got a region of memory that it wasn't supposed to, then it could be really important, sensitive information. It could have modified the behavior of something else at runtime. It could have done any number of things. This is how mods on video games work, by modifying regions of memory. So it halts the whole system, because if it doesn't halt the whole system, then it doesn't know that something hasn't been tampered with. It's a safety measure that's really important to prevent things like Heartbleed. And the idea is you code defensively so that you're not going to step out of bounds like that. You're not going to retrieve something from a region that you don't own or that's not allocated to your process. But in C and C++, this is notoriously difficult because it is low level. You have to control allocation and deallocation. You have to control raw pointers and things like that. Right? You don't have to, but that's commonly done. But it's notoriously difficult, even with really intensive scanning tools, to prevent this kind of thing from happening. So ultimately, oh yeah, that's right. Trying to regather my thoughts here. I think from here, I'll go over to the Windows post on this, or the Microsoft post on this, because they actually dive deep into the crash dump and look at the assembly code and kind of verify some of what Crowdstrike is saying here. I initially, when I heard about the Crowdstrike vulnerability, I thought it was a hack. I thought it was someone successfully gaining access that they shouldn't have. And the hearing that it was a out of bounds memory access didn't calm those fears, because that's exactly the kind of thing that a hacker would try to do. But I think the crash dump analysis here and the other analysis that I've seen does go a long way to calm those fears. You can see in the assembly code. They talk about trying to first check for null. So this already refutes some of the misinformation that was out there that, oh, it's from a null pointer dereference. No, the assembly code specifically checked for a null value in the register that it was reading from before proceeding. So it wasn't a null check problem. The problem was if you're not familiar with assembly code, these like R8, I think I saw R10 down here, R9, all of those are CPU registers. They're places where the CPU can stick data that it needs that it doesn't want to take the time to write to memory or something like that. So they're really fast places that you can access values. And so it was reading from, Microsoft says, the R8 register. And I believe when it talks about checking for null, I think it's this test R8. I think that's the null check. I'm not very familiar with assembly code, but I do know a little bit. But I think that's the null test that it's talking about. But I ultimately don't know which one of these is the operation that would lead to trying to use the address in R8 in that register. And then that leading to the out of bounds access, because whatever was stored in R8 was not the memory address that they thought it was. It was the junk data that came from the malformed file that led to some random region of memory, whether it be unallocated or allocated to something else. That's where the blue screen of death steps in. So the analysis from Microsoft helped. I don't think that it was a hack. Obviously, more information can come out later, but I think the conspiracy theorist may have quieted down somewhat about that. The key that really got me thinking about this, though, I'll skip all the way down to the very bottom, was a key part of the resolution to this. Here's how we prevent this from happening again. They specifically call out their investment in the Rust programming language. They have this thing they call their Secure Future Initiative, and they've recently added Rust support to the Windows kernel. This is what really got me thinking, okay, even before they said this, I was thinking, oh, could Rust have prevented this? But then if Microsoft is specifically calling out, hey, Rust could have prevented this, that adds a lot more weight to that opinion, I think. But honestly, from what I can tell from this and from everything else that I've read, and kind of looking at some of the misconceptions, like one of the big misconceptions was that, the file was full of zeros, but we have other people that have responded and said, well, no, my file is not full of zeros. It actually has contents. So it's, there was talk about, like I said, it was a null pointer dereference, or that, I don't know, all these different things. Ultimately, it doesn't really matter when you're thinking about, would Rust have saved you from those things? Rust does go a long way towards preventing the kind of blue screen of death error that we see here. But I have to point out, and a lot of other people have pointed this out too, it's not new. Nothing can prevent you from an issue like this if your team doesn't build up a culture of care and caution, taking advantage of the tools that your language ecosystem provides, and covering your software with comprehensive analysis and testing. Rust compiles to a position-independent executable. I can't remember if no, I don't have, I thought I had a page pulled up talking about that, but no, they compile to a position-independent executable, which means its memory addresses are a lot shorter because it uses address space layout randomization. So already you have to deactivate a default feature if you want these predictable memory addresses that you can just shove into a binary that gets linked or executed. Rust also includes boundary checks in things like slices or other types. It's actually in the assembly code. It will do a boundary check, or it'll include the size of the slice or things like that to guarantee that it's not going to attempt to access memory out of bounds. And the benefit of that is that it leads to something that is not a blue screen of death. It leads to a panic or an error, something that you can catch, something that you can handle and recover from in your software, as opposed to a blue screen of death that takes everything down with it. So Rust does a lot built in to kind of prevent that kind of situation in normal situations. And then a lot of people will point out that Rust allows you to override that. You can tell Rust not to protect you, but I would argue that that's a very explicit thing. It's something that you do right up front. Any code that is unsafe has to be wrapped in an unsafe block, and so it's really easy to spot in code reviews. If you have a team that is prioritizing safety and protection in their culture, then these kind of practices, these kind of that kind of explicit disabling that you have to do goes a long way, because you bring the eyes of the code reviewers down upon you in that situation. But if you have a team that allows frequent exceptions to these protections, if you just sidestep them when they're inconvenient, if you don't really take advantage of those tools that Rust provides, then you're not really even gaining anything from Rust's guards, and your team probably shouldn't be using it in the first place, because it's wasted complexity at that point. You're not using the complexity for what it's there for. But ultimately, the truth is, we don't really know what Rust would look like in the kernel. I mean, I know there are some, but Rust in the kernel is brand new. You can see it was just recently baked into the Rust kernel. I looked around in a few different places to try to find some details about how Rust would work in kernel mode, and I couldn't easily find it. I'm realizing I'm showing off a browser window here that you couldn't see yet, but this is the post announcing Rust being introduced to the kernel. It was in Canary. It was in just the beginning of testings a year ago. So it's brand new. We don't really know what Rust would be like in kernel mode, but I think if you choose Rust because you have a team that wants to prioritize safety and is building their workflows, their design patterns, their configuration in a way that encourages comprehensive care, and Rust is just a reflection of that priority in the area of programming, kind of reflecting that priority in all the other areas that they care about, then your team is much more likely to take advantage of Rust's protections. It's much more likely to spot an unsafe keyword in a code review and reject it, and let's find a different way to handle this. If your team is conscientious and takes care, then these features can work together to help you. But if your team is taking shortcuts, if nobody cares, if they're trusting the process a little too much, trusting the tests that they ran initially when they first deployed instances of that template type, and then not rerunning the stress tests later, for example, then it's not a magic tool to force them to be safer programmers. It's not going to make a bunch of difference in the grand scheme of things. I think there's a lot of factors at play here that have nothing to do with Rust. Like I said, stress testing each new template instance before it's released, or doing a gradual rollout with a canary phase where you could have said, oh, hey, 1% of these machines have gone down. We can no longer reach them anymore. For example, like, that would have done a lot to prevent this. And that has nothing to do with Rust. That is your team's practices, your team's policies and procedures. So no. Ultimately, the answer is Rust would not have made the CrowdStrike outage impossible. It's merely a tool that a safety-conscious team can use to make it harder to do the wrong thing, as part of a more comprehensive approach to their entire engineering workflow to prioritize reliability and performance. I think it's a tool, and it depends on how that tool is used. But if you're using that tool in the right way, it makes it a lot harder to do the wrong thing. And that's powerful. I think that's why Microsoft calls out tools like Rust as the answer to situations like this. Not because Rust is a silver bullet that will immediately slay the dragon, or the werewolf, I guess it would be, but because Rust is a tool that a safety-conscious team can use to make it harder for them to do the wrong things, and to make it more likely that they'll do the right things. All right, 45 minutes in. I didn't really want this to go this long, but I'll try to breeze through the rest of the articles that I wanted to talk about a little bit more. They're less dense. The first two articles were definitely the thicker ones. So the next topic that I'll talk about is CubeCL. Now, this is, I think, a really exciting project that's coming out of the Burn Deep Learning Framework team. Burn is a framework kind of similar to PyTorch or TensorFlow that helps you conduct machine learning AI operations in a way that is composable, in a way that is well controlled. You can put pieces together to build exactly the kind of flow that you need. You can take advantage of pre-trained models and fine tune them just like you could in PyTorch or something like that. But it's flexible. It has multiple backends. It can work with PyTorch. It can work with its own backend. And therein is the origin of CubeCL. So this was announced by the Tracel AI team. As they were working on Burn, they came up with this, and for really good reasons. But what it is a way to program your GPU, which is the really core piece of any kind of AI workflow, the tensors, the streams or arrays of numbers that GPUs are really, really good at. This CubeCL allows you to program your GPU directly using Rust. So you can use Rust's zero cost abstractions, the really optimized memory layout that it creates, to create really maintainable, flexible, and efficient compute kernels. And so this is a way to allow your code to run in GPU mode, essentially. But it's even more powerful than that, because this is all about the intermediate representation that they came up with as they were trying to make these back-end operations spread out to different back-ends. They wanted, I'll scroll down here. Yeah, they wanted to support things like CUDA, WebGPU. CUDA is NVIDIA's platform for custom GPU programming. Metal is Apple's platform for GPU coding. ROCm is AMD's platform. Vulkan is another platform that we use on Linux. So essentially, they want these operations to be portable across all of these backends. And so CubeCL is a way to write those optimized compute kernels in a way that's portable across different hardware. And so to do that, they created a just-in-time compiler. They have these three features. They call it automatic vectorization, comp time, and auto tune. So I'll skip down a little bit and go into each of those features a little bit more. The automatic vectorization that they mentioned first is really about how we have to work with data when we're working in AI flow. We send the data into the GPU as streams of numbers, and we get back more streams of numbers that have been adjusted and impacted by the weights that were stored in the model. It's all vectors, it's all tensors all the way down, essentially. And so vectorization is optimizing those tensors, putting those tensors together in a way that you can effectively parallelize the execution of it. You can structure that data so that you can handle batches of it effectively, and it automatically helps you vectorize it in just the right way to combine the streams together in just the way that you need to get the data out that is useful to you. And comp time is a way that you can basically set up plugins that execute at compile time. So they talk a little bit more about it down here. It says it's a way to modify the intermediate representation at runtime. So you can apply behaviors, macros, things like that when you're compiling a kernel for the first time, that initial compile. And then auto tuning is down here a little further. Auto tuning is a way to pick just the right runtime, the runtime that's going to execute the best on your system ahead of time dynamically, so that it can pick the best kernel to run on the best hardware. This is important because you're not always going to know where your code is going to be deployed. This allows you to test it and decide based on your testing which kernel to use on this particular platform. And so it makes it really portable. Their idea behind it is that it's more than just an optimized compute language. They say it's really the basis of high performance scientific computing in Rust. And that's what made Python the AI juggernaut that it is things like NumPy, the scientific computing that Python provides. And that's one of the things that has been missing in Rust, is that really powerful scientific computing library or tools that they aim to begin providing with this. So it's really like they started it as part of their back end for Burn for the AI workflows, but they're recognizing this is something that have vast application outside of that as well. There's a lot of different types of use cases that this would be really effective for. So I have not written GPU kernels myself, but I'm very fascinated by it. I think that I may try to do it one of these days here soon, especially playing around with something like CubeCL to gain an understanding about it. And so if that interests you too, or if you have interest in new AI machine learning workflows in Rust, like the Burn framework provides, check out CubeCL. It's definitely an exciting innovation, I think, that this Tracel AI team is working on. All right, next up, we have an article from the Rust Foundation. They have a Q2 2024 recap. So the Rust Foundation is the foundation that they do all kinds of different things to support Rust and keep Rust running. And this calls out just as a small part of that work that they did in Q2. And I didn't know they were doing so much. I love that they're posting these updates because it's filling in some things that I was totally ignorant to, I think. So first off, the first thing that I'm not sharing my screen, am I? That's something that I'm going to have to get used to doing again. Almost there. All right. Yep. I hit the wrong button before. This is the recap that I was looking at from Rebecca Rumble as part of the Rust Foundation. First off, they call out the launch of the Safety Critical Consortium, which is really interesting. I have this pulled up here. It's a group of different companies, Atacore, ARM, Ferris Systems, Oxide OS, High-Tech EDV System, and Woven by Toyota, which I had not heard of Woven, but I've certainly heard of Toyota. Essentially, it's the use of Rust in really safety critical software, in cars, in hardware, in all kinds of different things where safety is much, much more important than it typically is because people's lives are at stake. So they're working on collaborating with those different companies and the community as a whole to advance Rust and help Rust adapt to those kind of safety critical areas that it can be used in, because we think it can provide a whole lot better safety than the C and C++ implementations that you'll often see in those areas. Definitely interesting to see what comes out of that. They also call out that the Rust Foundation itself was mentioned in 27 news stories across the globe and across news media worldwide. And so it shows that interest in Rust is growing and it's gaining national attention. It's not just programmers that are becoming aware of Rust, but it's people who are interested in software and IT in general. They also navigated the Rust call for proposals for RustConf. RustConf sounds really exciting. I'm not going to be able to attend this year, but I wish I could. It's going to be in Montreal. They reviewed the proposals, they selected speakers, and they're beginning the process of setting everything up. It's soon. It's a little more than a month away. So I'm excited to see what kind of videos come out of that. And we've got a great list of speakers lined up. I considered proposing a talk around using Rust for AI, replacing PyTorch workflows with Rust. Chris Biscardi is great. I follow him on YouTube, and he has a lot of things around things like the Bevy engine. Yeah, great list of talkers lined up for RustConf, so check that out. And I also talked about what they had planned for in Q2, what else they're doing. They talked about John Bowman, the new software engineer lead at the Rust Foundation technology team. He's working on moving C++ interop forward and meeting with various stakeholders around that. And they're also stepping up their focus on security, especially after the XZ backdoor vulnerability. I don't know if you haven't heard of the XZ backdoor. I've got a note in here. It's the XZ utils library, and it's a really fascinating story, horrifying story. Someone literally spent 2 years cozying up to the XZ utils developers, gaining their trust, contributing value, and then suddenly pulled the rug out from under them and inserted some malicious code that really was drastically it allowed remote code execution. So those are some of the worst kinds of vulnerabilities. They can take over your whole system with that. So they're reviewing all of the Rust infrastructure, even though the XZ utils didn't really have anything to do with Rust. It's a very similar to a lot of the things that the Rust community is doing. And so we need to take the same kind of precautions that the C and C++ community is taking after the XZ utils vulnerability. And finally, they talk about the community grants program and the fellowship program that they are working on and is now open for applicants. So if you're interested in that, check it out here. All right. Next up, I've got, what is it? 2 more stories. Okay. 2 more. This one I thought was interesting. This one is from Veetaha, lead developer at Elastio, and it's how to do named function arguments in Rust. And this is one of the things that I miss from Python. Veetaha presents a Python snippet here, and there's the greet function here, and it's called with 2 arguments that are preceded with names, name equals Bon, age equals 24. This is a way to pass arguments out of order by name. So you can see if this function greet had age first and name second, this would still work just fine because you're calling the arguments by name rather than by position. And you can set up defaults for named arguments that weren't specified, things like that. It's a really ergonomic way to make your functions a little bit easier to call. And it's not something that Rust has. Rust only has positional arguments. And the ways that we work around that aren't always very ergonomic. So Veetaha calls out what I typically do. And what I've seen developers elsewhere, like in the Burn framework, for example, you'll create a struct representing the arguments of the operation that you want to perform. So, for example, this greet function, this is really simplified. You wouldn't do that with something that only had 2 properties, but think about something that had 20 or 30 properties that you needed, like an AI model config or something like that you need in order to initialize it. And so creating a struct to represent all that helps tame the complexity there. But it's a little bit ugly. You've got to reference all of the params there all the time explicitly. You can't omit certain parameters like you can in named arguments with Python. Although you can, as they point out, you can implement default, or you can derive default, and then you can pass in this spread of everything else from the greet param struct. So in their case, they've got this job, and the default value of any option is always none. So this implicitly initializes the job param at none. And so if there were any other params, they would have to support default. They would have to implement the default trait, but then they could be spread in implicitly here. But this still is a little bit ugly, and Veetaha calls it out. Things like typed builder can help, but you still have to create a struct for your params in order for something like typed builder to help. So Veetaha's solution is Bon, a builder that can act just on a function. So you can imagine the builder generating a struct representing these properties internally, and then creating this builder. It uses the builder pattern to allow you to call named arguments essentially by using builder methods on the struct itself. and then ending it in a call. So the call says, okay, all my arguments are done. Now do the thing. So this is similar to what typed builder does, but typed builder requires you to create a struct first like this. And Bond can do that too. Bond is designed to be the builder that you need for all build needs. And so it does the same thing that typed builder does on that too. But the distinctive is that it can do it on plain functions as well and eliminate the complexity of defining the struct itself, because it just derives the struct based on the arguments of the function that it decorates. I think it's a nice way to easily make a function into a builder, and it can handle the other things that you typically create as a builder. This is similar to, again, going back to the Burn framework, because I've done a lot of work in its source code, how it'll have config builders that it automatically derives, but they're using a custom macro in Burn to do that. This would be a reusable macro that you can use in a lot of places to do the same thing on any kind of type, not just a config or something like that. I like the idea a lot. I think, honestly, I'm okay with creating structs and implementing the methods myself, but I can definitely see how this cleans it up and makes it a lot easier, and you don't have to think about that aspect. It's a trade-off, though. Like, if somebody is not familiar with the builder pattern, they might come in and think, what in the world? Where did these methods come from? How is this all of a sudden here? They would know that the macro had something to do with it, but they wouldn't really understand what's happening behind the scenes and how it works. So there's pros and cons to that. Think about your specific use case, your team, the experience level of your team, the people who are going to be coming behind you to decide whether you want to use something like this or not. All right. And then finally, my last post. This is from Matthias Endler, someone with more than 20 years programming experience. So they've accumulated some opinions over time, just like I have. And this is an opinion that I particularly agree with. I see this in a lot of different places, not just in Rust, but in Go and elsewhere, where you have a prelude. It's a bunch of types that are automatically imported implicitly behind the scenes. You don't have to think about it. Result is one of those types. You don't have to import standard result before you can use it. That's because of Rust's built-in prelude. So you will often see other libraries following that same kind of pattern, providing their own preludes. CORM is one example of that. I'll go find CORM really quick and show what I'm talking about. It might take me too long to find the spot that I'm talking about, but essentially, when you are setting up an entity in CORM, it gives you a prelude that you import. Maybe if I just type prelude, I can find it. Yeah, there we go. Well, not really. This is all the things that the prelude brings in. Here we go. This is what I was looking for. That's an example of a prelude. You're importing a glob, a star. You're importing everything in prelude without any real explicit understanding of what's in there. So all of a sudden, you have values in your namespace that you don't directly know where they came from just by looking at it. And that can be confusing. That can be tricky. You might have preludes that step on each other and both define the same type that you try to break into your namespace, and all of a sudden you've got a compiler error. The article from Matthias kind of talks about why it's a problem, why a lot of people consider preludes and glob imports to be anti-patterns. And they understand why. They understand why it's there. It cuts down on some boilerplate, but it also can make things confusing when especially when you're using multiple preludes at the same time. You can get the same effect essentially by just importing a whole module. So, for instance, instead of standard format debug, you might just use standard format and then refer to format debug. I use this pattern all over the place. I have my modules organized so that they're not repeating themselves. They're very clear. You can use the module name and then the property within the module in a way that's very clear where it came from. And it helps you track the origin of things without resorting to really long names. Because like you might call this format debug instead of just debug. And then if you were referring to it from the module, you would say format debug. And so you're repeating yourself. Essentially, that's the kind of thing that I avoid. I name things with the intention that if you're only using one thing that's named that way, you can import it directly. If you're using multiple things that are named similarly, import the module so that you've always got that prefix and you know which debug or which thing that you're talking about in the namespace. Then Matthias goes on to talk about re-exporting comment types in your root. So that's kind of structuring your API to make things convenient to find. They talk about why there are some good examples for them, but I'm still of the opinion that they're not the greatest pattern. They're not the best habit to get into, and they're better to avoid when you can. All right, I think I should stop talking at this point. I've filled in a lot of the stuff that I've been reading lately. I'd love to hear what you thought about. I'd love to hear which of my opinions you feel like was wrong or was uninformed. I didn't spend enough time researching. Let me know what you think. If you've got a recent article that you'd like me to talk about, you leave a comment on this video or reach out on Mastodon. If you're interested in working with me, I work with a company called Nearform Commerce, based in Ireland. They're a great company. I love the people that I work with, and I'm definitely interested in bringing some Rust work to the company. If you would like to work with me, let me know. But I really appreciate you watching. I'm going to keep this up every week. I'm going to do this both for me and for everyone else who is interested in my opinions on things. And keep watching. I appreciate it. And have a great day.